Hello, I'm Steve Hammond, and I'd like to talk to you about the application and implementation of PAT to solid dose continuous manufacturing. So who is Steve Hammond? I worked for Pfizer for 39 years and had global responsibility for development and deployment of process analytical technology in Pfizer Global Supply Organization. That's the manufacturing division of Pfizer. I also had global responsibility for material science and forensic analysis support for the Pfizer Global Supply Organization. I am an internationally recognized expert in process-based measurements, PAT, and material sciences. I also have extensive experience with advanced manufacturing systems, including continuous manufacturing. So the contents of my talk today are going to be an overview of the continuous system that I was responsible for. And I want to talk about fiber optics in flowing powders because they're what a lot of the PATs are based on. I want to talk about simulation for rapid PAT development. I'm going to talk about PAT applied to wet granulation, PAT applied to coating, and a little bit about mass balance models as a PAT. So an overview of PCMM really has to begin with the control and release strategies for continuous manufacturing because they are actually merged, because a lot of the PAT and release strategies are actually the control strategy. The use of PATs at the end of each unit operation, dispensing, mixing, granulation, drying, milling, compression, coating, provides the basis of the control system, as well as a means to achieve real-time release. And the value of real-time release is enabling a more flexible and lower inventory supply chain. Here is the Pfizer continuous rig, and you can see this rig has two halves. On the left-hand side, there's a direct compression line. On the right-hand side, there's a wet granulation line. Now, those are actually combined together for the last stages of wet granulation, where the granules that have been produced are turned into tablets. Also, there are a coating unit in this rig as well. And the PATs I want to describe, I'm showing here where PAT1 is generally to look at primary mixing, PAT2 is to look at the twin screw wet granulation where the granules are formed. PAT3 looks at the characteristics of the granules that we're producing. Are they dry? Are they milled correctly? In fact, to begin with, we did put an extra PAT in there, an FBRM system for looking at granule size. PAT5 is about the probe put into the feed frame of the tablet press, and I will describe this in quite a bit of detail later on. And then there were two PATs developed for the coating system, coating thickness measurement, and then looking at the elegance of the tablets that have been coated. So I want to talk a little bit about fiber optic probes in a flowing powder. So here I'm going to show the near infrared probe that we've tended to use inserted into the process. And on the right hand side you can see the probe. It's a very fast scanning instrument that uses fiber optic probes, and the probe is inserted here into the feed frame of the tablet press. And on the left hand side the same type of probe is inserted into flowing powders, just generally moving down a pipe. But the mechanism for getting good spectra from these fiber optic systems is the same. And I do want to talk in a little bit of detail about them. So what I'm showing here is detail of how the fiber optic probes that we've been using interfaces with the powder. And I want to draw your attention to the diagram on the left, where it's showing the amount of powder that interacts with the probe and how the light comes out of the probe, goes into the powder, and then has to get back into the fiber optic probe. Now, the thing about that process is that while it's going on, only 3 milligrams of powder are contributing to a spectrum if the powder is stationary in front of the fibre optic probe. Now, that is a problem because we want to assess a powder going through a continuous system in terms of its ability to produce a tablet of a specific weight. In other words, we need to understand content uniformity at a tablet weight. And the way we get around this problem of a small amount of material contributing to an individual scan is in fact to take multiple scans while the powder is moving, which of course it is in a continuous system, and to average the signal we get from, say, 50 scans. Now, the spectrometer is very fast scanning. It can collect a scan in 10 milliseconds. So it doesn't take long to do this. So that's the approach that's been taken. We scan multiple times with the powder moving, so the powder is refreshed in front of the probe as we take the 50 scans. And by integrating those 50 scans together, we can say the spectrum that we're getting represents a unit dose weight. So I just want to show you some evidence of the poor sampling that you get with these fibre optic probes if the sample is stationary. And on the left-hand side of this plot, you can see we scanned a powder, actually we scanned it 10 times in the dish, and we moved the powder between each scan. And then we tried to build a calibration from the powders of different strength. In fact, there are 7 different strength powders here from those single scans of a stationary powder. And you can see it's very, very difficult to get a good performing calibration. And that really is this problem with very, very small sample size if you have the powder static. Now, if you look at the right-hand side here, where we've moved the powder in this device that is actually a rotating chamber with powder in it, that's, in fact, it's a simulator for the feed frame of a tablet press. If we did as I described before, move the powder, scanned 50 times and average those 50 scans, the calibration then build is very high performing and very satisfactory indeed. So it shows the value of understanding how the probes work and understanding what you need to do in terms of the environment the probes are in to make them perform in the way that we would like them to. I'd now like to talk about the use of the near-infrared placed into the feed frame of a tablet press. So here is the direct compression system that I want to talk about, and the probe is actually inserted into the feed frame of the press you can see there. A bank of feeders are feeding powder into a mixer, which is very small. It's mounted onto the top of the feed frame, and it's difficult to see in this diagram. So here's a close-up of the probe inserted into the feeder of the tablet press. And as you can see, as the powder circulates in the feed frame, the spectrometer is doing, as described before, it's collecting multiple scans and integrating them as the powder passes in front of the window of the probe. And here's some evidence that that approach actually works. If you look at this plot here, the black line is the powder feeding through the tablet press feeder, and in this case the powder is being fed through at 5 kilograms an hour. Now, we also wanted to check whether the response from the probe was affected very much by the throughput through the whole system, and so the blue line represents the speed, a throughput of 30 kilograms an hour passing through the feeder system. The little red crosses, they represent where a tablet core was sampled from the tablet press and taken away for HPLC analysis. So you can see the ability of the near-infrared to constantly monitor the concentration of the active ingredient in the blend is extremely good and is very tolerant of different throughputs through the system, provided the speed of the spider wheel in the feed frame is kept reasonably constant. So here I want to show you two time plots, and these are the output of the near infrared in the feed frame. So the top plot is showing you the concentration of the API in the powder as it's passing through the feed frame. The little blue dots are telling you where samples were taken and analysed for HPLC and correlate very well with what the near infrared is telling us. Now the bottom plot is very interesting because for this product the contact uniformity of magnesium stearate was important. And here you can see the near infrared is constantly outputting the concentration of the magnesium stearate and showing that the control system has it well in control. I want to now talk about the idea of simulating that environment of the feed frame and speeding up the development of PAT applications. I want to introduce you to the feed frame simulator, and here you can see on the right hand side this device. It's mobile, it can be put on a bench top for experiments to be completed. And what this is one of the body of a feed frame that's been simulated and copied and put into a mobile frame for us to be able to use in a laboratory environment and understand the performance of fibre optic probes and indeed develop calibrations for the probes in this environment away from the tablet press and using the minimum amount of material. In fact, all you need to fill this feed frame is about 80 to 100 grams of powder. If you look at the picture in the middle, you can see it has a bottom exit valve that is very precisely controlled and has a hygiene bottle clamp on the feed frame to allow us to do flow through measurements if we want to. We can feed the powder in the top of the feed frame, it can come out of the bottom, and we can see what the effect of the fibre optics probe is as we do that. The diagram on the left-hand side shows you the main cavity of this with a viewing window and the control of the bottom exit valve. So inside that feed frame there is a rotating paddle wheel which are identical to those that are actually in the commercial manufacturing tablet press. Work has been published by Pfizer on the use of the simulator to develop calibrations remotely from the tablet press that can actually run in commercial manufacturing. In fact, in this case here, what was desired was to develop one calibration in the simulator that would work on two identical tablet presses in one location in the USA and another location in Germany. So what was done was a 15-point DOE using the simulator, and various blends were made with the ingredients from both locations and data collected to make that a calibration with the intent of working on both tablet presses. The DOE consumed only 0.05 kilograms of API and only 1.8 kilograms of the excipients. So this is a very material sparing approach for making near-infrared models that are very effective but not interfering with the use of the tablet press or requiring excessive amounts of material. So here's evidence that this approach of using a simulator to produce calibration models actually does work, because this is a plot of the near-infrared response to the model that was constructed in the USA in the simulator and actually running on the commercial press in Germany. And you can see the pink dots where tablet cores were taken and analysed by HPLC, are showing an extremely good correlation to the near-infrared model that was made in a simulator 3,000 miles away. And now I want to talk about wet granulation. And just to remind you, there's compact feeders feed material into a mixer that then that mixture is fed into a twin screw granulator. The material has water injected into it, it's granulated, and then goes into the dryer that you see on the floor here, the inverted cone. So feeders through a mixer into a granulator where water is added and the granulation takes place, and then the granules are dried. I want to talk to you about the mixer and the near-infrared interface to the mixer that we used on the Pfizer continuous rigs. And to illustrate how this system works, I'm illustrating an exercise that was performed to look at the resonance time distribution of the mixer. So this plot on the right hand side here is a time course where we ran different powders through the mixer and then looked at the response we got from the near-infrared. And to begin with, just the 4 feeders on the left-hand side here were activated and feeding powder. In fact, they are all excipient feeders. And so essentially the blue line you see at the beginning of that plot is a placebo blend passing in front of the near-infrared. Now, just for 5 seconds, the active ingredient feeder was turned on and a shot of API put into the blend. And you can see the response of the near-infrared, where the peak in the response appears and then decreases because the feeder was only turned on just for a few seconds. This shows the sensitivity of a near-infrared to be able to look at the primary mixing of powders, particularly in a continuous manufacturing system. Now, the interface for the near-infrared probe at the outlet of that mixer is something that will be talked about in another AUSTAR meeting later on. After the powder has been mixed, the next stage is to feed that powder into the twin screw granulator, and you can see in this slide a picture of, or at least a diagram of, the twin screw granulator. So the powder is fed in and water is injected into the powder, and then it goes through a kneading process between the twin screws. What we needed to do was to find a way of looking at the granules as they were exiting the granulator to understand how well the granulator was working. And by the way, there's a picture on the left hand side here of the granulator and the granules that are outputted. So here's the output that we gained from a near-infrared that was placed into a device where the granules are captured in front of the probe window and allow us to get very, very good spectra of the granules as they're coming out in a stream. Now, the plot here looks very noisy, you would think, but in actual fact, the oscillations you see are really the true variation in the water content of granules that are exiting the granulator. And in this exercise here, we ramped up from 15% to 18% moisture, so you can see the mean point of each of those oscillating areas is where we'd expect it to be. And as the granules are exiting, they're showing that the water is indeed at the right level, but it is quite variable in terms of its distribution, which is very important to understand that in terms of the performance of the wet granulator. After the granules have been formed, they go into a segmented fluid bed dryer that you can see on the right hand side of this slide. Once the granules are dried, they need to be milled, and the device you can see in the middle photograph is the milling area. And what we wanted to do was to understand two things about the granules: were they completely dry after going through the dryer, but also when they were milled, were they milled to the right particle size distribution? And you can see the type of spectra that can be collected from that probe inserted in, just below the mill. And the diagram you can see shows the effect of unmilled material, milled once material, and then very finely milled material. The probe is actually able to quite well, qualitatively at least, tell us whether the mill is milling these granules as they normally would do, and also to tell us what the moisture content is, which is often the two are related. Here I'm just showing the near-infrared spectra collected on the output of the mill, just so you can see how well the different levels of milling are separated in the near-infrared spectra. I've already talked about the formation of the tablets and how we use the feed frame to do that. Once the tablet cores have been made, they're coated, and I will just want to show you a little bit about the technology used for monitoring coating. The continuous rig that we had at Visor had this type of coater. You can see the cylinder at the top is feeding in uncoated cores, and at the bottom coated cores will exit. There are actually two parameters that we're interested in when tablets have been coated. One is the thickness of the coating, and the other is elegance of the coating. What's the appearance of the coating? Both of these techniques, the Raman on the left and the optical coherence tomography system on the right, use the ability of light to go through the perforations in the inner drum of the coater and get snapshots of several tablets as they're passing by the beam of the two probe systems. Essentially, they will provide an mean thickness of the coating, because several tablets will contribute to that data that's being collected. But it is an effective way of measuring coating thickness. Now, optical coherence tomography has been particularly good at showing us the boundaries between the inner core and a coat and the outer edge of the coat, as you can see in the green circle here on this slide. That optical coherence tomography is very good if you've got multiple layers, because it can distinguish the boundary between each of the layers. This diagram illustrates the two probe systems and how they're situated into the coater. Now, on the left-hand side, the tablet elegance system is based on a camera that uses something called grazing optics, that is, light that is shone at a very low angle to the surface of the tablet and emphasizes roughness of the coating and allows images to be computed that can actually give a digital readout of the relative coating roughness of tablets. I want to just talk about mass balance or RTD models and a hybrid approach for using those models along with PAT for the control system of a continuous system. A number of companies are starting to deploy this, and you often hear them described as engineering models. They're based on the load cell data on the feeders and actually the mixer, which in the Visor system is also on a load cell. We can use those load cells in the generation of mass balance calculations. That is, the amount of material going in should equal the amount of material coming out of a system. And calculating those provides us with an independent means of looking at blend constituent concentrations and predicting them from the weight data. But the one thing about the load cells is they are very good if everything is going as expected. The one thing they're not so good at is detecting transient fluctuations, particularly in the feeder performance or the mixer performance. But those fluctuations are very well detected by the PATs, the spectroscopy part of these hybrid models. The near infrared is capable of picking up very, very subtle changes in the concentration of any of the ingredients that are passing through the system. But a hybrid approach which is being taken that combines both of these measurements of quality is actually turning out to be a very, very effective way of monitoring continuous manufacturing processes. I must acknowledge the people that have contributed to the presentation that I've just provided, particularly from the MPAC group in Pfizer Global Supply, where I was working. That's Chi-Chi Chen and Ki Hong. And from the SPECAC group within Pfizer Global R&D, particularly Angela, Elizabeth, Sonia and Andy. But also a lot of the work that we did in terms of prototypes for measurement systems in the feed frame were very significantly assisted by the University of Ghent, and I must thank Professor Thomas de Beer and Fien de Leersnyder for their contributions to this presentation. I thank you for your attention.